Welcome to The Explainer. Today we're diving into a really cool evolution in how we build massive AI models. It's a story that starts with a clever shortcut and ends with a mathematically beautiful solution for training AI at a scale we've never seen before.
And that question right there, it's not just a cute metaphor, it is the central challenge for AI architects today. You see, as these models get bigger and more complex, taller if you will, making sure they don't just collapse on themselves is everything. And it all begins with the most basic building blocks.
Okay, so to really get our heads around this, we have to start with the foundation of pretty much every modern AI. And that foundation is a clever little trick called the residual connection. This simple skip connection was an absolute game changer. Think of it like an express elevator for information in that AI skyscraper. It helped solve this massive headache called vanishing gradients, which basically let us build models that were way deeper, and because of that, way more powerful than ever before.
But, and there's always a but, this brilliant idea came with a really frustrating trade-off. Depending on how you built it, you were kind of stuck on this seesaw. One version, pre-norm, fixed the gradient problem, but then your layers could become redundant, kind of useless. The other version, post-norm, helped with that redundancy, but oops, you risk bringing the gradient problem right back. The root issue? The connection was rigid. Its strength was fixed.
So this annoying seesaw problem, it got some researchers over at ByteDance thinking, and they asked a question that would completely change the game.
And their answer was a big, resounding yes. They came up with a new way for the network to figure this out all by itself. They called it hyperconnections, or HC for short.
So instead of that one rigid shortcut, hyperconnections creates this multi-lane information highway. The network itself actually learns how much signal to send down each lane, dynamically mixing and routing information to find the absolute best path for performance. It's not just a dumb skip connection anymore. It's a smart, adaptable transit system. Pretty cool, right?
And wow, the results were seriously impressive. Models that used hyperconnections learned almost twice as fast and scored way higher on tough benchmarks like the ARC challenge. It was a clear, undeniable win.
But there was a catch. As the models got bigger, and the training went on for longer and longer, a new, dangerous problem started to show up. Those skyscrapers started to show some serious cracks in their foundations.
I mean, imagine this. You're training a massive model for days, maybe weeks. Everything's looking perfect. The loss is going down smoothly, and then, bam, this happens. The training suddenly goes haywire, and the model's performance just catastrophically collapses, wiping out all that progress in an instant.
So what on earth was going on? Well, it boils down to this number. Researchers dug in and found that the signal inside the network was being amplified by up to 3,000 times. That's not a typo. 3,000.
And that's the real kicker here. The very same flexibility that made hyperconnections so powerful, it also became its greatest weakness when you tried to scale it up. That information highway had no speed limits, no guardrails, and eventually the traffic would just pile up into a massive, explosive crash.
This instability is where researchers at DeepSeek-AI enter the story. They saw what was happening and developed this incredibly elegant refinement, a way to keep all the power of hyperconnections, but finally tame its wild side.
They did it by introducing a new rule based on a mathematical concept called a doubly stochastic matrix. Okay, now don't let the name scare you. You can just think of this as the ultimate set of guardrails. It's a mathematical guarantee that when the network mixes all that information between its different lanes, the total amount of signal energy stays exactly the same. No explosions, no vanishing signals, just perfect, stable flow.
So this new method, they call it mHC. It keeps all the awesome benefits of that flexible, multi-lane highway, but it adds one simple, powerful new rule. You have to conserve energy. This brings back the critical stability you absolutely need for these giant networks. And when you see the results, well, the difference this makes is just crystal clear.
All right, so let's put these two architectures head to head. We're talking a massive 27 billion parameter model here. And the difference in stability? It's literally night and day. Just look at this. On the left, you've got the original hyperconnections, and you can see that signal gain just exploding, rocketing off the charts. Now on the right, you have mHC with those mathematical guardrails, and look, that signal is kept perfectly stable, right around a value of 1 across every single layer of the network. It's rock solid.
And here's why that stability matters so much. It translates directly to better performance.
You can see it right here in the benchmarks. mHC doesn't just avoid collapsing, it consistently beats both the baseline and the original hyperconnections. It doesn't matter if it's complex reasoning, reading comprehension, or general knowledge. The new, stable architecture comes out on top. It's not just more stable, it's just plain better.
Okay, so after all that, what's the big picture? What should you really take away from this whole journey? From a simple connection all the way to a mathematically constrained one.
It's really a classic story of scientific progress, isn't it? You have a foundational idea with a limitation. Then, a powerful but ultimately flawed solution comes along. And finally, a principled mathematical refinement delivers a robust, scalable architecture that actually gives us the best of both worlds. It just goes to show that how we connect the pieces of an AI is every bit as important as the pieces themselves. This whole evolution, from that simple skip connection to mHC, it really proves that as we build more and more powerful AI, the answer isn't one or the other, it's both. The real key to unlocking that next level of scale won't just be about making bigger components. It will be about these deep, principled innovations in stability. That's the foundation that's going to let those skyscraper AIs reach incredible new heights and unlock more powerful and more reliable tools for all of us.